Motional EMF on a metal bar. A conducting bar is moving through a uniform magnetic field at constant speed, as shown. In which direction will there be a magnetic force on the conventional charges in the bar? We're going to use our right-hand rule, and we're going to say that the conventional charges, so I'm getting my right hand out here, conventional charges are moving towards the top of the page, and the field lines are pointing toward the camera. Which way are we going to pat to the right? There's our rationale for that. The pat right-hand rule for the magnetic force on conventional charges: if your thumb is pointing toward the top of the page and your right thumb is pointing that way, and your right fingers are pointing out of the page, you are going to pat toward the right. Now, which portion of the bar will have a higher potential than the other portion? Well, that means that the right portion of this bar is proportionally going to have more positive charge, and the left portion will have more negative charge, and so the right side will have a higher potential. Now, what's the magnitude of the EMF induced between the ends of the bar here? What we have done, as we've just said, there was a magnetic force on the conventional charges or on the conducting electrons. It doesn't make any difference. But the point here is that this side will have a higher potential, so I'll put a little plus by it. And the side on the left will have a lower potential, so I'll put a negative there. And what we are ending up with is there is a magnetic force. Let's just take the conventional charges. There is a magnetic force that is directed to the right on conventional charges, FB. And if this is moving at a constant speed, then there will be inside the bar, there is an electric field you see now that points to the left. So there's going to be an electric force on the conventional charges toward the left, where that is going to be numerically equal to that. So what we have is we have an electric force that's numerically equal to the magnetic force, since we're moving at a constant speed and things aren't changing anymore. What's the magnitude of an electric force? It's equal to Q times E. What's the magnitude of a magnetic force? If everything's at right angles, it's Q times V times B. The Q's cancel, which means that the strength of the electric field that we've generated is equal to, now that's not the question. The question is, what's the EMF? If we use Faraday's law says that an induced EMF is equal to, and I'm just talking magnitude now, we won't worry about the negative sign, which involves Lenz's law. The magnitude of the induced EMF is the change in magnetic flux, but it's also equal to the path integral of E dot dl. And we want the EMF, so this is the guy we want right here. And we know an expression for the electric field right here is V times B. I'm going to cross that portion off, I think. And V is a constant, B is a constant, which means then I would just have to integrate dl. Well, when you integrate dl, look here in the lower right, isn't that just L? The strength of the EMF is going to be V times B times L. So that's going to be, I'm looking at the units here, and that's the right unit for velocity, and that's the right unit for magnetic field, and that's the right unit for length. So I'm going to be a little bit lazy, and I'm going to leave that off. And when you crunch that out, you're going to get 8.1 volts.